So we can discuss something from the diesel cycle, how we can solve the problem and its PV diagram. So coming on to the diesel cycle, it is a constant pressure cycle. So why it is called as a constant pressure cycle? Because the heat addition take place at a constant pressure process. So the diesel cycle is called the constant pressure cycle. So see this. So while calculating the air standard efficiency of a diesel cycle, here the air as a working fuel. So this efficiency is always less than, sorry, it is always greater than the actual efficiency. That is, actual efficiency is always lower than the air standard efficiency. So see these values here. The generally the efficiency is equal to work done by heater, that is output by input. For some of the standard values I have given to solve the problem. Since this video is motto only to solve the problem rather than concepts. So the adiabatic index, what is adiabatic index? Gamma. That value is 1.4, and Cp, that is specific heat capacities at constant pressure and volume, that is denoted as Cp and Cv respectively. For Cp, the value is 1.001 kilojoule per kg. So here a mistake. For Cp, the value is 1.001 and Cv, that is 0.717. So the mistake is in unit, that is kilojoule per kg Kelvin, that is kj slash kg k, that is kilojoule per kg per Kelvin. Kelvin is also included, please correct that mistake. So for Cv, its value is 0.717 kilojoule per kg per Kelvin. For the diesel cycle, the compression ratio is not equal to the expansion ratio. Here the heat is added at the constant pressure process, and the maximum temperature of the constant pressure cycle is T3 and the maximum pressure is P3. So I have already mentioned this video is rather teaching the concept. It's a video how to solve the problem in a very systematic manner. So we can see the PV and TS PV diagram of the diesel engine. See this, the process 1 to 2, it is an isentropic compression process. That is, it is an initiation process. Here 1 to 2, 1 to 2, from the PV diagram we can infer that it is a constant pressure process. So in that process heat is added. So the value of P2 and P3 will be same. And 3 to 4, it is an isentropic expansion. And 4 to 1, isentropic means reversible adiabatic process. And 4 to 1, it is an isochoric process. Why it is isochoric process? Heat is rejected at the constant volume process. So from this PV diagram, we can infer that the P2 and P3, that is the pressure at the initiation of the compression and the pressure at which the fuel is added and the pressure at which the fuel is on the fuel addition completes, remains same, and volume at which the process is completed and the volume at which the process is initiated will be same. That is, V1 is equal to V4 and V2 is 2 is equal to P3. So from this, V1 minus V2 is the stroke volume. This is up to the clearance V2. V2 is also known as clearance volume, and V1 is also called as cylinder volume. So some of the adiabatic relationships, that is PV to the power gamma is equal to a constant, TV to the power gamma minus 1 is equal to a constant. So I have explained process 1 to 2 is an isentropic compression, 2 to 3 is an isobaric expansion, 3 to 4 is an isentropic expansion, and 4 to 1 is an isochoric compression. And see this B stroke, that is stroke volume, which is equal to V1 minus V2 if the volume of initial and second volume is given. If the bore of the cylinder and the length of the crank is given, then the stroke volume is pi by 4 into d square into L. So compression ratio is V1 by V, that is cylinder volume divided by clearance volume, and expansion ratio is V4 by V3. Here the new ratio called cutoff ratio. Why it is called cutoff? Here the fuel is cut off at the point 223. So we call it as cutoff ratio. That is usually described as a Greek alphabet rho. So V1 is a cylinder volume, V2 is a clearance volume, and V1 minus V2 is a stroke volume. So with this information we can proceed for solving the problem. So isobaric relationship, PV is equal to nRT, where P is constant. So V by T is a constant. For diesel cycle, P2 is equal to P3. Q added is equal to MCP T3 minus T2. Q rejected is equal to MCV T3 minus T4. So the mean effective pressure is work divided by Q added. How would you calculate the work? So work is equal to heat added into efficiency. That is the value of work. So work is Q added minus Q rejected. Work is equal to efficiency into Q added. For diesel cycle, so this is not an actual theoretical proof I have given. So that is T2 and T4 are approximately equal. The value will be multiplication of lower temperature limit and a higher temperature limit taking the root. That is the value. That is T2 approximately equal to T4, which is approximately equal to root over T1 into T3. So this is not an actual, but it is a way to find the answers that you have get is right or wrong. That is, this may range in the value. If the T4 is 600 Kelvin, T2 may range from what 585 to 610 or 615 range. Okay. So this is the overall efficiency of the diesel cycle. That is, neta diesel is equal to 1 minus 1 by gamma into 1 by Rc to the power gamma minus 1 into rho to the power gamma minus 1 divided by rho minus 1. That is, there is a derivation called air standard efficiency of a diesel cycle. So using some of the adiabatic relationships, you may derive this equation. What is rho? Rho is a cutoff ratio. Rc is the expansion ratio. What is the formula for rho? Rho is the volume after fuel addition to volume before fuel addition. Fuel addition take place at 223. So rho or gamma is equal to V3 by V2. So RC is the adiabatic compression ratio, that is V1 by V2. Gamma adiabatic exponent, rho is cutoff ratio. So with this informations, we can do a problem. So in an air standard diesel cycle, so air standard diesel cycle, the compression ratio is 16. They have given the compression ratio. And at the beginning of the compression, that is, the compression take place at 1 to 2. So at the beginning of the compression, that is, temperature is 15. So here see this RC is V1 by V2 is equal to 16. T1 15 degrees Celsius. So in the air standard problems, we usually convert the centigrade to Kelvin. This is the standard result. And the pressure is, and at the beginning of the compression, the temperature is 16 degrees Celsius. And at the beginning of the compression, the pressure is 0.1 megapascal. That is, P1 is equal to 0.1 megapascal. Heat is added until the end of the constant pressure process. That is, constant heat is added until the temperature at the end of constant pressure process is 1480. That is, constant pressure. In the PV diagram, we may see that the constant pressure process varies from 2 to 3, and the heat is added until the end of the constant pressure process, that is T3. T3 is the end of the constant pressure process. That value is going to be 1480 degrees Celsius. So they are asked to calculate the cutoff ratio, heat supplied per kg of the air, and a cycle efficiency. So the given values are descriptive. So first one, they are asked to find the value of cutoff ratio. So for finding the cutoff ratio, we need V3 and V2, or we have to find the expansion ratio. So we can find the cutoff ratio. Cutoff ratio is going to be V3 by V2. Here the 2 to 3 is a constant pressure process. So we can take V by T is equal to a constant. So we know the value of T3 and we want to find the value of T2. So for finding the value of T2, we know the value of T1. So that one process 1 to 2 is an adiabatic expansion compression process. So we can write one important relationship is there. Tv to the power gamma is minus 1 is equal to constant. So that is T is inversely proportional to V gamma minus 1. So we write from the upper temperature to lower temperature limit T2 by T1. Since it is an inverse temperature relation, we write the inverse of the volume. So V1 by V2 to the power gamma minus 1. So what is V1 by V2? Yes, it's given in a question. Compression ratio. Compression ratio is cylinder volume to the clearance volume. That is the compression ratio. So we write the value of that as 16. So gamma as an adiabatic index. So 0.4. That's value is going to be 873.5 873.502 Kelvin. So next one, the asked is the heat supplied per kg of air. That is, for 1 kg of air, how much heat is supplied? So the M is 1. This is MCP T3 minus T2. Heat is supplied, that is T3 minus T2, 1.005. So next one is, we know the value of T3, but the T4 is unknown. So using the value of T2, we can find the value of T3. Or using the value of T3 and we can find the value of T4. But if you write T4 by T3 is equal to V3 by V4 to the power gamma minus 1. What is the value of V3 by V4? Yes. Here we may use the help of an expansion ratio. Expansion ratio is V by 4 by V by 3. So if we take the reciprocal of this, we may get V3 by V4 is equal to V3. So we know the compression ratio is a ratio of compression ratio, cutoff ratio is a ratio of compression ratio to the expansion ratio. So we know the value of compression ratio and we know the value of cutoff ratio, and finally we can find the value of Re. That is, here we want the inverse of Re. So we have taken 1 by Re is equal to 0.1255 to the power 0.1. So we find the value of T4 as 764.256 Kelvin. So here find using that value we find the Q added. That is, in same way we can find the value of heat rejection. That is heat rejection. So in the same way we can find the value of Q rejection. What is Q rejection? What is Q rejection? That is M C V T3 T4 minus T1. So using some of the adiabatic relationships, we can find the value of T4 T4 and substitute in the Q rejection. We may find the answer. And the last one is overall efficiency. So for efficiency, you know the formula neta is equal to 1 minus 1 by gamma into 1 by RC to the power gamma minus 1 into rho to the power gamma minus 1 divided by rho minus 1. So using that all the values are find out, and the compression ratio is already given. So no issues. So you will get the answer either 0.6133 or 61.33%. So with this I have concluded my presentation. So thank you.